Welcome to this explainer, everyone. We are about to unpack one of the absolute most fascinating puzzles in human behavior and economics. Have you ever wondered why a store can slightly raise the price of one item and literally nobody seems to care? But if they touch the price of another item by the exact same amount, sales just completely collapse. Well, today we're diving into the invisible force that drives our everyday buying habits. So, why does a 10% price change sometimes create an absolute tidal wave of consumer reaction, and other times it barely makes a ripple? It's a mystery that businesses spend millions of dollars trying to solve. We react so drastically to some price changes while we completely ignore others. But why is that? To get to the heart of this puzzle, think about airline tickets versus table salt. If there's a 10% drop in the price of airline tickets, you see a massive 40% surge in the volume of tickets bought. People are suddenly packing their bags, right? But with table salt, that exact same 10% price drop results in a tiny, almost invisible 0.5% shift in quantity. No one rushes out to hoard salt just because it's a few cents cheaper. Here is our roadmap for this explainer. First, the mystery. Second, the core definition. Third, the 5 degrees. Fourth, point versus arc. Fifth, the percentage method. And finally, total expenditure. Section 2, core definition. So, price elasticity of demand is formally defined as the degree of responsiveness of quantity demanded of a commodity to a change in its price. I really want you to focus entirely on that word responsiveness. That's the golden key to this whole thing. Are we highly responsive when a price changes, like with those airline tickets, or are we practically unresponsive, like with the salt? Section 3, the 5 degrees. Now, let's look at the extreme edge cases of human buying behavior, which, to be fair, are pretty rare. Imagine a completely vertical line on a graph. This is perfectly inelastic demand. It represents complete stubbornness. Whether the price is high or low, the quantity demanded remains exactly the same. Think of a life-saving medicine. Price doesn't matter. You just absolutely need it. Now, contrast that with a totally horizontal line. That represents perfectly elastic demand. At one specific price, consumers will buy an infinite amount, but if the price goes even slightly higher, demand drops to absolute zero. It is complete, infinite flexibility. Mathematically, we anchor these extremes with two simple values. For that stubborn, vertical, perfectly inelastic curve, elasticity of price, or EP, equals zero, just zero responsiveness. For the horizontal, perfectly elastic curve, EP equals infinity, infinite responsiveness. Okay, let's see how this translates into realistic, everyday scenarios, the ones you actually encounter in daily life. First, we have relatively inelastic demand, which has a very steep curve. A large drop in price causes only a little change in demand. This is typical for basic necessities. We need them, so price drops don't make us buy vastly more. But then we have relatively elastic demand. A 10% drop in price leads to a much larger, say 20% increase in demand. The curve is flatter and highly responsive. This is where luxuries like vacations or expensive jewelry live. The mathematical thresholds for these real-world behaviors are super simple to remember. For those rigid necessities where we just don't react much, EAP is less than 1. For flexible luxuries where we eagerly jump on a sale, EAP is greater than 1. Which brings us to the fifth and final degree, the perfect equilibrium. It creates this beautiful curve known as a rectangular hyperbola. This is unitary elastic demand, where EP equals exactly 1. It means a percentage change in price yields the exact same percentage change in quantity. So if the price falls by 10%, demand rises by exactly 10%. It's a very rare, perfectly balanced state in economics. Section 4, point versus arc. So how do we measure elasticity for infinitely small changes at a particular macroscopic point on a demand curve? We use Marshall's point or geometric method. The core visual formula you need to know right off the bat is this. Elasticity of price equals the lower line segment divided by the upper line segment. Let's break this into two distinct segments to see how it works. First, imagine a linear straight line demand curve AB, touching the y-axis at A and the x-axis at B, with point D sitting right in the middle as our midpoint. If we calculate elasticity at 5 separate points on this single line, here's what we get. Up at point A, the vertical intercept, it's AB divided by 0, which equals infinity, perfectly elastic. At any point E above the midpoint, it's BE divided by EA, which is greater than 1, relatively elastic. Right at the midpoint D, it's BD divided by DA, equaling exactly 1, unitary elastic. Down at any point C, below the midpoint, it's BC divided by CA, making it less than 1, relatively inelastic. And finally, at point B, the horizontal intercept, it's 0 divided by AB, which is 0, perfectly inelastic. Now for the second segment, what if we have a nonlinear curved demand curve? Well, to find elasticity at a specific point, let's call it R, you just draw a straight line AB tangent right through that point. Because the slopes are identical at that exact point of contact, the elasticity simply equals the tangent ratio, BR divided by RA. Section 5, the percentage method. Here is the master formula. Elasticity of price equals the percentage change in quantity demanded divided by the percentage change in price. This simple ratio gives us the exact EP numbers we were just looking at. If the top number, the quantity change, is bigger than the price change on the bottom, your result is greater than 1, meaning it's elastic. If the top number is smaller, the result is less than 1, meaning inelastic. It really is just that simple. Section 6, total expenditure. I want to walk through an example with you because this creates a real aha moment. Imagine the price of something is 60 and we buy 10 units. Total money spent, 600. Now the price drops to 50. Because it's cheaper, we buy more, 12 units now. But check out the total outlay. 50 times 12 is still exactly 600. When a price drop is perfectly offset by a volume increase, total spending stays exactly the same. That tells a seller that the demand here is perfectly unit elastic. If you graph this, you get two distinct rectangles. The first rectangle represents the spending at the higher price, and the second is the spending at the lower price. Because total spending remained at 600 in both cases, the geometric area of those two rectangles is perfectly equal. But what happens when demand isn't perfectly balanced? Let's contrast two financial outcomes. For a relatively inelastic good, a price drop from 60 to 50 might only increase sales from 10 to 11 units. So total spending actually falls from 600 down to 550, the seller loses money. But for a relatively elastic luxury good, that same exact price drop causes sales to surge from 10 to 13 units. Total spending rises from 600 to 650. The seller makes more money by lowering the price. Visually, this translates directly to the graph. For inelastic goods, as price drops, the geometric area representing revenue literally shrinks. But for elastic goods, dropping the price makes the new rectangle physically expand. The area is greater, representing that incredible surge in total revenue. Application, pricing strategy. Okay, so here is the ultimate cheat sheet for any seller. If you are selling an inelastic product, like a basic necessity, lowering your price just lowers your total revenue. To make more money, you actually raise prices because people still have to buy it. But if you are selling an elastic product, a luxury, raising prices will absolutely kill your sales. To maximize revenue on flexible goods, you lower prices to capture a massive surge in volume. I'll leave you with this final high-stakes question to ponder based on everything we've just covered. If you were setting the price for a life-saving medicine, a perfectly inelastic good, versus a luxury vacation, a highly elastic good, how would elasticity dictate your pricing strategy? Would you lower the price to drive volume or raise it to maximize revenue? Understanding consumer responsiveness really is the key to unlocking that answer. Thank you so much for joining me for this explainer, and keep learning.